Why does the sound of a siren change as it passes by? Why does starlight shift color as it travels towards or away from Earth? It's because of the Doppler effect. You may be familiar with this equation from school. The wavelength observed equals the actual wavelength plus or minus the velocity of the source times the period of the wave. You may have seen the frequency version like this. The wavelength controls how we experience the wave. Hence, when an object is moving, we experience a pitch change of sound or color shift of light. Let's break this down quickly. Here's an object. Every second, it emits a wave that travels at 1 meter per second. Here it is at 1, 2, and 3 seconds. Now let's consider what happens when the object is moving. Let's say at 1 meter per second, the same velocity as the waves. Here it is at 0 seconds. After 1 second, the object has moved to where the first wave has reached. After 2 seconds, it has moved again, and the next wave was emitted from its previous position. Here's 3 seconds. The old waves continue to expand out from where they were emitted as the object continued to move forward and emit new waves. The result is an expansion on one side and compression on the other of wavelength. On one side, the observed wavelength is the actual wavelength plus the distance traveled by the object in one wave cycle. This distance equals the velocity of the object times the wave's period, t, the seconds it takes a wave to complete a cycle, because velocity times time is equal to distance. On the other side, the observed wavelength is the actual wavelength minus this velocity times the wave's period. Okay, here's the question though. What happens when the object is passing by you from a distance? Well, you're not just going to observe the wavelength from one side or the other. You will experience all the wavelengths in between. Hence, the nnyyyoommnn sound that you hear. How do you calculate that? It helps to draw a diagram. Here's the line representing the path of the object. This line, d, is the distance between the observer and the object's path. The perpendicular line gives the shortest distance, so this angle is 90 degrees. Now, it's the velocity that the object moves towards or away from us that determines the new observed wavelength, correct? But in this scenario, that's no longer the velocity of the object. For example, right when the object passes by d, it's not actually moving away from us at all. Instead, we can think of this new velocity called the radial velocity as the rate that this length h between the observer and the object is increasing or decreasing. Can you think of a way to calculate this distance? Yes, we can use Pythag. H equals the square root of d squared plus L squared. To get h in terms of time, let's say t equals 0 where d intersects L. Plug in velocity of source times time for L. So here's our function for h in terms of time where v and d are constant. You can see as time goes on, this function looks more linear because in our triangle, as L approaches infinity, h approaches L because it gets closer to being a straight line parallel to L. So as time approaches infinity, where d and v are constants, our function, the square root of d squared plus v times t squared, approaches v times t, a linear line. Here's the mathematical way to write this. This is something I wouldn't have predicted, so it's cool how thinking about the situation a function represents reveals its behavior. I wonder if you could apply this elsewhere by thinking of a situation that some equation could represent to predict what its graph could look like. In y equals v times t, the slope or rate of increase of h is the velocity of the object. Let's just see this in action here. If we plug in 2 for velocity, we see a slope of 2. But what about before the graph approaches this linear line, when it's still a curve and the triangle is still triangle-y? How do we calculate the rate of change of h then? We use the derivative, which for those not familiar yet is the function that inputs x and outputs the slope at x. It does so by finding the slope between 2 points as they get infinitely close. I will not be going into the calculation, but the derivative of our function for h is this. So this gives us the rate that h is changing at any given time, or the radial velocity. This is its graph. I just plugged in arbitrary values for our constants, which you can see on the left. We see the radial velocity approaches the velocity of the source as time goes to infinity, and when the object passes us at t equals 0, it is 0. like we discussed before. And if we plug this function back in as velocity in our old equation for observed wavelength, we get our new equation. Let's graph it, again with arbitrary values for our constants. Now we can see exactly how the wavelength we observe changes over time. At t equals 0, it's the same as the actual wavelength. When the object is far enough away, the wavelength observed approaches our original equation, again because d gets less significant. We see with these values for the constants, the object doesn't actually have to be that far for this to happen, only around 10 seconds away. And in the passing periods, it goes through a range of wavelengths, finally explaining the nnyyyoomm sound. Let's change our constants to match the scenario we observed earlier on. The velocity of the wave and the object were both 1 meter per second, and the object emitted a wave every second, so t equals 1. Now, for our distance to the path of the object, which we didn't look at before, I'll just keep it at 5 because I like 5. It matches what we've seen. On one side, the observed wavelength is 2. This is what we observe when the object is far ahead of us and we are standing over here. On the other, it's 0. In the middle, it's the actual wavelength 1, and here are all those wavelengths in between. Wow. If we make d longer, we see it takes more time for the graph to reach its horizontal asymptotes, which makes sense because it takes more time for h to approach L. If we change the velocity, the change in wavelength increases or decreases. Changing the actual wavelength shifts the graph up and down. Increasing the period of the wave also makes the change in wavelength increase because the object can travel farther in one wave cycle. All of this is so exciting. We are able to represent a complex seeming phenomenon from everyday life clearly in this graph. Throughout this video, we've seen how representing a problem visually helps make it approachable. Often, we have the abilities to explore questions that initially seem too complicated. And we see the true value of graphs for fully understanding a situation. Digging deeper into a common physics equation took us down an interesting and rewarding path of geometry, interesting graphs, problem solving, and some calculus. This goes to show how math can be used to view a problem from all sorts of vantage points, find underlying patterns, and gain new insights about day-to-day occurrences. I hope you enjoyed this video as much as I enjoyed creating it, and I'll see you in the next one.